Hello everyone, my name is JaeYoung from XXL Lab. Today I would like to introduce a paper published at CVPR 2025 titled Atom Aligning Text-to-Motion Model at Event Level with GPT-4Vision Reward. This work addresses a key challenge in text-to-motion generation, which is how to ensure that the generated motion accurately reflects the detailed structure of the input text, especially at the level of discrete events. Text-to-motion models aim to synthesize human motion sequences based on natural language descriptions. And recent models have shown success in generating motions that are visually plausible and semantically aligned with high-level descriptions. However, when the input text contains multiple structured events with explicit order, frequency, or dependencies, existing models often fail to reproduce these final-grained details correctly. This misalignment becomes a major issue when models are applied in contexts that require interpretability or precision, such as embodied agents, digital characters, or human-computer interaction. Previous methods typically rely on contrastive running, sequence modeling, or heuristic loss functions to run the mapping between text and motion. While effective in some settings, they share several limitations. First, they lack an explicit feedback mechanism that evaluates whether the generated motion fully reflects each aspect of the text. Second, most evaluation methods do not assess how well a motion follows the internal structure of the instruction, such as the number of repetitions or the order of events. And third, human annotated preference data used in reward-based fine-tuning is expensive to scale and often lacks consistency and structure. These limitations point to a need for an automatic, scalable, and fine-grained supervision signal that can guide motion models towards more precise alignment. Now let me walk you through the core methodology of Atom in more detail. The framework consists of three major stages: data construction, reward extraction, and reinforcement learning based fine-tuning. Each of these plays a critical role in aligning motion generation more precisely with event-level instructions. And we begin with the data construction stage. The authors first curate a diverse set of text prompts that are intentionally rich in event-level structure. These prompts include multiple sequential actions, repetitions, and dependencies that test the model's ability to understand not just motion categories, but also the relationship between them. To accompany each prompt, the authors generate multiple motion sequences using an existing text-to-motion model, especially Motion GPT, which published it at NeurIPS 2023. These sequences are not labeled manually. Instead, the labeling and supervision come from the next stage using GPT-4Vision as an evaluator. In the second stage, the model takes a novel approach to reward extraction. Here, each generated motion is rendered as a series of sampled image frames, and these frames, along with the original text prompt, are fed into GPT-4Vision. But instead of asking for a general judgment, the others provide GPT-4Vision with specific evaluation instructions. The model is asked to assign scores along three axes. The first is integrity, which checks whether all key actions mentioned in the prompt are actually present in the generated motion. The second is the temporal order, which evaluates whether those actions are performed in the correct timing. And finally, the third is frequency, which asks do repeated actions occur the correct number of times. GPT-4Vision is guided to reason across both visual and textual information and outputs a numerical score for each of these dimensions. These scores form the basis of the running signal in the next stage. The final stage is reinforcement running based fine-tuning. Instead of using traditional supervised objectives or contrastive rows, the others employ a method called inverse preference optimization or IPO. This is a gradient-based reinforcement learning technique that optimizes the model to produce outputs which receive higher scores under the learned reward function. By using GPT-4Vision's feedback as a structured reward, the model runs to improve its performance not just on average motion quality, but on alignment with the intent and structure of the text instruction. An important detail here is that the face model is not trained from scratch, and it is a strong pre-trained generator, and Atom fine-tunes it using relatively lightweight methods like LoRa adapters combined with reinforcement updates. This makes the training efficient while still yielding significant improvements. So overall, Atom's method is distinguished by its use of large vision language models, not as generators, but as automated reward providers that evaluate motion in a structured and interpretable way. This architecture allows the model to receive feedback that is much closer to how a human might evaluate whether a motion truly matches a given instruction. To support this framework, the authors built a novel dataset called Motion Flipper. It contains over 80,000 text-to-motion pairs, each paired with GPT-4Vision-derived scores on integrity, temporal order, and frequency. And this dataset enables large-scale training and evaluation of event-level alignment. For evaluation, the authors use standard metrics such as FID, multimodal distance, and R precision. They also measure diversity and multimodality to confirm that the model maintains generative expressiveness. Crucially, they rely on GPT-4Vision's structured scores to assess alignment accuracy, which goes beyond conventional metrics. Experimental results show clear improvements. The Atom-tuned model outperforms the baseline across multiple axes, including FID, alignment accuracy, and diversity. To summarize, Atom makes several contributions. It introduces an event-level reward framework based on GPT-4Vision. It presents a scalable method for evaluating and improving motion text alignment, and it provides a new data set that can serve as a benchmark for future work. More broadly, this paper demonstrates that large vision language models can be used not only as generators but also as structured evaluators and learning agents. This opens new directions for controllable generation, not only in motion synthesis but potentially also in video animation and robotics. In conclusion, Atom represents a meaningful step forward in aligning motion generation with language at a fine-grained, interpretable level. Its use of GPT-4Vision for automated event-level reward is both innovative and practical, and the proposed framework is likely to influence future research in this domain. Thank you for listening.